Bismillahirrahmanirrahim. Dear student, welcome you all in lecture 6, lecture 10, sorry. In this lecture basically we are trying to complete the remaining part of cutoff points and cutoff bars. So basically here we will basically discuss the uh, some kind of theoretical approach which is explained in Nilson book, and as well as trying to cover some theoretical portion of mgregor book. So this is a kind of continuation of the lecture 9. Okay, in lecture 9 basically if I want to recap some of the part of those lectures, so basically we are did the calculation relating to that how we can calculate theoretical cutoff points. Okay, here we are trying to explain that understanding a little bit further. Okay, and basically we are trying now to that how actual cutoff points are achieved. Okay, those discussion is just relating with the theoretical cutoff points. Okay, now we are trying that what kind of effects are produced, in a beam when the bars are cut. Okay, so basically from this basic equation which is written like here, that the tension force in a steel, you know, the tension force in a steel is equals to what is equals to you know mm, bending moment divided by the lever arm. Okay, this basic equation which is written like here, this is the basic equation. We all know the this equation that area of steel is equal to moment divided by Fy into d minus a over 2. Clear? Now this d minus a over 2 is basically what it is, lever arm. Clear? Lever arm is what we all know, the stress distribution in a rectangular beam. That at the lower portion there is tension force in the steel, and in upper portion there is a compression in concrete. Clear? And this compression is basically at a distance of a over 2. Clear? And this whole thickness is basically you know a. Clear? And distance from the neutral axis uh, to the centroid is known as c. So this is basically the flexure theory, and you must need to recall the design of rectangular beam, that what is the basic mechanics, how they design a rectangular beam. So the distance between these compression and tension is called JD. Clear? And the distance from the top fiber to the of the beam to the tension center is called D. Clear? So if you want to obtain this distance will be equal to D minus A over 2. So lower arm is equal to D minus A over 2. So what is the moment? From this equation you can easily get moment, that moment is equal to force multiplied by the lever arm, because a couple is giving you, this is tension force and this is moment arm, that is JD. So the multiplication of these two will give you a couple, bending moment. So M is equal to tension is multiplied by JD. Clear? So from this you can say that P equals to moment divided by JD. Clear? And further we know that T equals to in a bar AS into Fs equals to moment divided by JD. So this is the basic equation. Now in this equation we know a very basic relationship that, for example, JD is remain constant. There is narrow changes are occurring along the length of the beam. Basically, along the length of the beam, there is narrow changes. But if we ignore these those changes, and we just assume this JD constant, then we can directly say that tension is proportional to bending moment. Clear? Now this is the basic relationship, right? That along the length of the beam, the tension force in a steel, the tension force in a steel is directly proportional to moment along the beam length. Clear? So once moment is increasing, this means your tension force is increasing. So as you know, in a simply supported beam, the bending moment is maximum at the center. So we can directly say that your whole tension force will generate at the mid-span, and thus bending moment from the top, like this diagram you will achieve. So this say that there is the maximum moment, that is W is square by L. Clear? So from here you can say that the moment is decreasing. So at this point one can say that tension will be proportional to the moment which is right there. So as this moment is less than this one, so this tension force will also be less than this one. If I assume that this is at T max, so this T will be less than T max. Clear? And thus you can say that the stress produced at this point in the steel will be lower than the stress produced will be there. So if we ensuring that there is our tensile stress in the steel at this point reaches to Fy, clear? Reaches to Fy, or we assume that stress is equals to Fy. So this assumption will not be true at this point, because there you can say that Fs will not equals to Fy, clear? Because the moment at this point is lower, and as we can say that tension is directly proportional to bending moment. So therefore if you are providing, for example, if you are providing 4 bars there, and those 4 bars are yielding at this point, at this moment, because the moment is maximum, but at same 4 bars are continued to this point. Clear? They are continued to this point. So these 4 bars, you can't say that they will be yield at this point. Why? Because moment is lower. Is less. If you want that these bars could be yield, okay? If you want that these bars should yield at this point, you need to, you need a little bit different approach. The approach is that because you need here that moment there, this moment should be there, okay? Then they will yield. So if this, as along the length the moment is decreasing, so we can't able to get this moment value at this point. So we have second option, and the second option is that we need to reduce the steel area right there. If we reduce the steel area, so you must know one other relationship, that moment is proportional to steel area. Clear? Moment is proportional to the steel area. So therefore, if this moment needs you greater amount of steel at this point, clear? So at this point, so as you can say, the moment is less at this point. So in proportion to this moment, if you want to yield this point, you need to reduce this s. So at lower value of m, you will get lower ast, and thus your yielding criteria will be ensured. Clear? And as well as the stress will also be equals to Fy. So basically this is the basic mechanism which you can say give birth to uh, cutting of bars along the length of B. Okay. To achieve this criteria, you can say we cut up the bars. Okay. To ensure the yielding criteria as well, and as well as it is also important for economy point of view. But remember that whenever you are trying to cut this point, the ACI other criteria is that if you want this yielding stress, you need to provide sufficient development length, because without that development length, that stress you can't able to produce that stress. One important criteria is also there that, for example, along the length of the beam, if you need, you know, if you need maximum movement like that, yeah, at this point you need, you know, uh, there is maximum amount of movement. Yeah. So at this point you need, you can say, full development length of the bars, because you are assuming that if y stress will be produced. So for yielding of stress, you need full development length to provide bars from the center to both sides of the beam. But as one can say, or we can assume that as the moment is here is, you can say, that is the one third. So as you can see that the moment is, if you assume that this is one third moment, so or you can say one two moment, or you can say 50% of that moment. So one can say that if this bar needs to be, at this bar need this at this point the bar needs to be 100% development length. So as the moment it gets reduced, so beyond this point, one can say that the development length must be equals to L by 2. Okay, because the moment is gets reduced to 50%. So the development length must need to be reduced L over 2. But although this theoretically you can say, but practically we will provide the full development. Okay, but theoretically this is true. Okay, so basically here the same theory is discussed by the Nilson here, and one of the most important things which he say there, that you must know that from this bar, in this rest of theory, he basically in this basically in this above theory, what he basically says that, for a simply supported beam, this is the moment diagram, clear? And one can draw, okay, this is the maximum point, and at this point basically he say that as this is the maximum movement point, so you need basically here 100% of steel, clear? 100% of steel you need to be required. And you can say there is 0% of steel to be discontinued. Means at this point you can't discontinue steel. Okay. So once you move along the length of the beam, your movement it gets reduced. So if I assume that this is my point, okay, where the movement is get reduced to 50%, where at the moment it gets reduced to 50%. Mhm. Mm. The moment it gets reduced to 50%, now at this point, if you want that, so at the moment get reduced to 50%, you need to reduce the area of steel at this point to be 50%. So here you see that if this is a scale, this is a scale diagram, you need to 50% area of steel required and 50% of steel to be cut off. Okay, means that at this point you need to cut up steel 50% of that steel which is you provided at the mesbah. Clear? And as at the support, okay, at the support, you need theoretically you need 0% of steel there because the moment is zero right there. Clear? So as moment is zero, so you theoretically you needed 0% steel. This means 100% of steel should be discontinued. Maybe you can say cut off at this point, 100%. This is a very important diagram, okay? And if this diagram is drawn on a scale, you can get the theoretical points. Okay, and this diagram is basically this is if you have a simply supported beam, okay, and that simply supported beam is basically subjected with a UDL, okay, with a UDL, so you can easily get the theoretical cutoff points from this kind of bars, and that bar is basically at a in this graph. Okay, you can see it is the end pages of the Nilson book, and this is graph here. This is a kind of scale diagram, okay, and this is the percentage of bars which may be cut off at any point. Okay, so if you want that you are cutting up your 50% bars, so you just need to select this point and just come down. Okay, once you come down, let's say this point is uh, 0.1, this point is 0.2, so these digits are 10. Okay, 1 2 3 4 5 6 7 8 9 10. So you can say this is around about 50% is around about 0.1, uh, 1 2 3 4 5 6, you know 6 0.167 roundabout. So you just multiply that 0.167, multiply it with the length of the beam, you can get the point, the theoretical cutoff point. We will use this diagram, okay. And if you have this not simply supported continuous beams, you continuous beams, so then you will use, and you are using coefficient method, and the continuous beams are arranged in equal spans with a UDL. Okay, so then we will use this chart. From this chart one can find out, one can find out, so at these from this charts you can get those theoretical points. Okay, we're trying to use this chart, inshallah. Clear? So this diagram is basically used for simply supported beam. Clear? And this diagram is basically used for continuous beam. Okay, there is negative moment, okay, and there is positive moment. These dot lines basically show the actual movement diagram. Okay, and uh, this line basically, this full line basically show the movement strength, or you can say movement required diagram, which is which is provided by the steel area, as we done in uh, Cormac book in lecture 9. So that is the movement strength envelope diagram. Okay, so it is provided by the steel, and it is achieved, this movement is basically achieved by the mechanics, by the engineering mechanics principles. Okay, and this maximum movement is W square, but this diagram is basically on the basis of phi mn, which is equals to, you know which is equal to uh, a is f1 into d minus a over 2. It is constructed on the basis of that formula. Clear? So here same scale is used, if you are uh, interesting to find out the cutoff point at which you are cutting your 50% positive state area. So just mm, draw this line and select this point and come down. From there you can select those fractions. Okay, multiply those fractions with the length of the beam, and you will get the cutoff points distance from the support of the to the cutoff points. Clear? So this is the same approach. Similarly, the same approach is followed for the negative state. You can select 50% state, and that point can be drawn to the to the span, to the length, to the beam length, and you can determine that how much distance that cutoff point for the negative state area exists. Okay, so this can be achieved by using the movement coefficients, as shown by the SIS. I will show you these charts. From these charts, you will just select the 50% of steel if you are interested to cut up, okay, and then select the graph and come down and select this fraction, multiply this fraction with the length, which give you the cut up distance from the face of the support. Okay, so we will use this approach. Okay, some practical considerations, we basically uh, used whenever we are calculating the theoretical cutoff points. So now we are moving towards our actual cutoff points. From up to, you can say, up to this point, we are basically concerning with theoretical cutoff points. Now we are approaching to uh, our actual cutoff points. Okay, theoretical cutoff points is basically, those, there are some restrictions on ACI. If the ACI impose some kind of restriction on theoretical point, and those theoretical points are extended, for positive bars towards the span, towards the supports, by increasing their length, okay, by some amount. And then when you increasing your cutoff points, your cutoff point distance, so then you can achieve your actual cutoff point. So those theoretical points will be right. Those different considerations which will be used, okay, we will use right there. Okay, so in lecture 9 and 8 I will mention you that point, that whenever you are cutting a bar, you know in a beam, whenever you are cut a bar in a beam, so at this theoretical cutoff point, there is very huge concentration of shear stress, and due to that shear concentration, because there builds a diagonal cracks, there are diagonal cracks are developed, and due to that crack, the whole tension is transferred to the steel, and no tension is taken by the concrete. And once this crack is built up, the effective cross-section area at this point of the beam will get reduced. And as the effective cross-section area of the beam gets reduced, so the shearing capacity of the section will be reduced. So if you are interested that this kind of shear stress concentration to be prevented, you need to extend, you need to extend this critical point to the actual point. Okay, and this distance is basically kept equal to d distance, or you can say 12 times our diameter effective depth, or this may be LN, the clear span divided by 16. You know, this approach is basically used. You select the maximum one value. From this, you will select the maximum value and add that distance with a theoretical cutoff area distance. So, theoretical point cutoff points will be extended to there, and then this point, this theoretical, this cutoff point is then called the actual cutoff point. Okay. Then we can say that this is our, although there are some other considerations due to which this point may be extended towards the support, but although basically we can say that this is our actual cutoff point. Clear? So this consideration is basically, this approach is basically adopted due to shear stress concentration. Clear? Now basically this point is adjusted in this shaded area. Clear? And similarly, AC, another uh, restriction is that, or another code criteria is that, further reflecting the possible change in peak stress location requires that at least one-third of the positive moment steel, one-fourth in continuous span, be continued uninterrupted along the same face of the beam, a distance at least 6 inches. This is a kind of integrity, they want some kind of integrity, If I show you this kind of discussion, basically this kind of discussion is right there, not there. This is integrity in steel, okay. That practically, because so much of time, that the beams are fed experience this kind of uh, rules are imposed due to experience, due to practical failures of structures. Those kind of restrictions are imposed by, you can say, by the ACI. And where is that point? Okay, this comes, this is, mgregor is clear, although it is in Nilson book also, but this is called structural integrity in reinforcement, because structural integrity in the reinforcement is necessary. You can say for a continuous beam, if this is your positive steel area and this is your actual cutoff points, you need to continue one-fourth area of this positive steel. For example, minimum 2 bars. If there are 8 bars, you need to continue minimum 2 bars, and this continuous area must be equals to or greater than 1/4 of this area. If here you are providing 4 square inches area, there you need to provide 1 square inches area. Okay, so this is one criteria. This is another criteria. It is important for structural integrity. Similarly, they say that there must be some bars. Minimum 2 bars must be continuous. Here must be 2 bars continuous. Okay. So the, for the case of, I think for the case of negative steel area, there must be 1/6 area must be continued, and there must be 1/3 area continued. Okay, at this point. And similarly, if you, this is for positive reinforcement, clear? And this is for, this is some other explanation. You see that this lower bar must be extended at the support up to a distance of 6 inches. Okay, you see that this insertion of the steel of the positive steel area into the support must not be less than 6 square, and similarly 1/4 area should be continued. Here you can see that this is 1/4. For simply supported beam, if we remove these supports and it is a simple support, then this area will be 1/3. Clear? Here you can see from the face, if the negative bars are coming from that side, so you need to continue that steel area, that is the H2 area, should be continued for a distance of LD, and the amount of steel right there, its 1/3 area must be continued to a point, this point, and this is the point of inflection. So from the point of inflection you need to continue the steel area for a distance of D 12 dB and L divided by 60, meaning the flat space. Okay? And similarly, this is the point of inflection. You need to continue the top steel area. How much top steel area? 1/3, 1/3, not whole area, not whole negative area, just 1/3 area of the negative steel area beyond the point of inflection for a distance of this much. Okay. So this is a kind of structural integrity, and you also need full anchorages, providing full anchorages, and similarly you need to extend for 6 inches. Clear? Uh, this is a kind of structural integrity, it is important. Okay. Now here we will discuss. Remember, this is also very important. Checks. Okay. AC basically do not allow you that you will cut the area in a tension zone. Yeah. If you are cutting steel bar in a tension zone, like one can see that this is a tension zone. So ACI do not um, allow you that you will cut the bar area in tension zone, but they allow you to cut the steel area if there are three criteria to be met. Okay, and these three criteria you can see. So we will explain these three criteria in our examples. Right at this point it is difficult to understand. Yeah? We will explain these three criteria, but not need to be fulfill these three criteria. Only one criteria is sufficient to fulfill. Okay, you have just only to check one criteria from this. So in Nilson book, these two criteria are basically adjusted. mgregor basically satisfy this criteria. Clear? So we check this criteria, and if these criteria are not satisfied, then you cannot, you can say you cannot cut off the area in the tension zone. Okay. So this is a very important discussion. Clear? Mm, this is one of the most important diagram, and you people must need to be to understand it. Okay, because this is important. This diagram is important. Clear? This diagram is important. Clear? Mm. This is, a moment diagram for a continuous beam. Okay, and for a moment diagram for a continuous beam, if it is a column, these are columns, and this is continuous beam. So most of time, if you see its bending moment diagram, it starts from the negative, comes to positive, then come down to negative, then it goes up positive, and then it comes down to negative. This kind of movement diagram. This is positive, this is negative. This both are negative, this is positive, this is negative. Clear? This is maximum negative movement, and this is uh, you can say this is the maximum. This is the maximum positive movement point. Clear? This is the maximum positive movement, and this is the maximum negative. Clear? Now this point at which the movement comes out to be zero, basically this is called inflection point. Clear? So inflection point is that point where movement change its signs, okay, from negative to positive or positive to negative. Clear? So this kind of detail you will see there, that this is the positive diagram, okay, and this is the negative diagram. Clear? This is the inflection point for positive steel, and this is the inflection point for negative steel. This is the center line of the beam. Clear? And this is the maximum moment capacity. This is the theoretical moment, okay, from the face, okay, from the face of the support. So there are some important things present in basically in this diagram. Clear? So there are some interesting things, okay, some interesting you can say knowledge in this diagram. Clear? What kind of information this diagram provides us is that you can see the beam there. This is the positive steel, okay. This is the positive steel. SEA code basically says that if there are total bars there, and you are interested to cut up the bars at this theoretical point, this is your theoretical point, and this is your the point which is at which the maximum moment is happening. So you need to provide your full positive area at this point. Clear? Now you need to extend your whole bars for a distance of L. Clear? This distance you can see that this distance is LD equals to LD, both sides, to this side as well and to this side as well. Your full bars must be extended from the peak point to the left and to the right, must for a distance of LD. Clear? Now what important information is there, that if it is your theoretical point, and if it is a theoretical point, okay, so if basically this point is your theoretical point. Clear? This is your theoretical cutoff point. So you basically, from previous discussion, I clear you that at theoretical point we do not cut the bars, we cut the bars at actual cutoff point. And where the actual cutoff point is at a distance of d 12 dB or ln by 16. ln by 16 is basically used for negative steel, but you can use it for positive steel, okay, but you get to select the maximum value. So this is theoretical point, so you need to extend toward the face for positive steel reinforcement, towards the face for a distance of 12 dB d or ln divided by 16. So this point is basically your actual cutoff point, and the distance from the actual cutoff point to the peak point, this one, it must be equals to or must be greater than LD. You see here that this distance from the peak point to the actual cutoff point, this distance must be greater than or equal to LD. Okay, your actual cutoff point, or you can say your actual cutoff distance, okay, must be greater than or must be equal to LD. Clear? This is important. Basically, this actual cutoff distance must be equals to or greater than LD. Clear? And the steel area which you cut there, and now the continuing area, the rest of the bar, area must be greater than, you can say, 1/4 of the total area, or the rest of continuing area must be equals to or greater than 1/4 of the total positive area. Clear? And that bars must be extended into a support for a distance of 6 inch. Clear? For a simple span, I already mentioned you, the continuing area is 1/3. The total, for example, if you are providing 6 bars there, your continuing bar, these continuing bar must be 1/3 of those bars. Like 1/3 of 6 is 2, so there must, and minimum 2 bars should be there. Okay, minimum 2 bars. Larger is possible, greater number of bars is possible, but minimum 2 bars should be continued according to ACI. And similarly, for negative reinforcement, you see this detail. Okay, that you need the bar which is coming out from this direction, there they should be continued for a distance of LD. Okay, for continued for a distance of LD, and then basically you can see this is the theoretical cutoff point for negative steel. If you down this theoretical point to the beam, you get this point. Now theoretically you need to cut your negative steel at this point, and that will be your theoretical cutoff distance. Okay, so theoretically you need to cut your bar there, but practically due to SCIM restrictions you can't cut the bar at theoretical point. You need to go for actual cutoff point. Now in the negative moment case, you need to go beyond, or you can say you go opposite from the face of the support. There you move toward the support. There you can go in opposite face of the support for a distance of 12 dB or ln by 6. Okay, so now this is your actual cutoff point. This is your actual cutoff point for your negative steel, and this distance is basically actual cutoff distance, for negative steel, and this distance must be equal to LD or must be greater than LD. And one other information it gives you, that the total negative area which you are providing there must be 1/4 area to be continued. 1/4 area of this total area must be continued for a distance of, for a distance of uh, LD. You see there, for a distance of LD from the theoretical cutoff point for negative reinforcement. This is the theoretical point for negative reinforcement. So from theoretical cutoff point you need to proceed for a distance of LD. Okay, this area will be 1/4. This area will be 1/4 of this total area. Means if there are 4 bar, so 1/4 becomes 1 bar. So not 1 bar, just 2 bar. You need to provide 2 bars continues to this point, and this point lies at a distance of LD from the theoretical cutoff point. Or you can say, for this is the point of inflection of negative movement. So from point of inflection, you need to continue steel this distance, for this distance, that is ln by 16 d or 12 dB. Like there we see that from point of inflection, no, not in this case, this only occur in negative steel area. So in negative steel area you need to provide extra steel beyond the point of inflection, for a distance of 12 dB D or L by 16. Okay, this is this area must be equals to 1/3. Sorry, I say 1/4, but this is 1/3. Clear? This extended steel you see right there. You see right there. This one. This one. This steel. This is this steel is 1/3. You know, 1/3. 1/3 steel must be continued for a distance of, this distance, which is from the point of inflection of the negative steel for a distance of 1/3 ln by 16 or d or 12 dB. Mostly we use these two, correct? And from theoretical cutoff point for a distance of LD. Clear? This is a very important information. This is detailing information. It must be ensured. ACI says this must be ensured. So in this diagram you can say a very important information. Okay, you must need to clarify yourself by this diagram. Clear? Mm, this diagram basically provides you some useful information. Okay, and this is, you can say, these are the ACI coefficients for cutoff paths for positive as well as for negative steel. When these coefficients are used mostly in field, basically we use these coefficients. Most of the people use. Okay, even your laborers do not know about the ACI, but they use these coefficients. They cut these bars. They say 1/3, 1/4, 1/3, 1/4. So these coefficient works out. Okay, for cut-up bars or for bent-up bars, both these are used. You know what these are coefficient. There are some restriction of ACI that these spans must be uniform. This span length must be equals to this. There are some, I think so. This is 10%, 15% difference in these loading as well as in span lengths exist. So ACI allow you. Otherwise, ACI do not allow you. Okay, and these beams must be subjected to UDLs. Okay, not point loads. So if these beams are subjected to UDL and these spans are uniform, you can use these coefficients also. Okay, so for negative reinforcement, you see that this length L1 by 4, this will be the actual cutoff point, and this is 1/3, 1/3 for a DDL. It is 1 add for this length divided by add, and this length divided by add. The bar should be extended for a 6 inches. The bar should be extended for a 6. This is for bent up bar. You need to bend bar at a 45-degree angle and at a distance of L1 divided by 7, and 1 is this length. Clear? And this is L1 by 4th. You need to bend bar at a distance of L1 by 4. Okay. And similarly, you need to extend the bars for 6 inches. So this diagram is also very useful, but they work for uniform spans and uniform UDL loading. Clear? Not for other type of loading. Clear? So basically, these are some special requirements near the point of zero. Uh, mm, Basically, this diagram is very useful diagram. In this diagram, there is very important information. Okay, and I would like to extend the this lecture. I would like to stop this lecture up to this point. Okay, because from this point, this is a new topic. Okay, this is a new topic because this is the point of inflection, and now at point of inflection you need to provide some sort of special arrangement. Okay, so we will discuss it in lecture 11. Okay, inshallah we will continue our lecture beyond this diagram. Clear? and you will see that what this is a kind of other restrictions from ACI. Okay, and after that inshallah we will start to know numericals. Okay, so basically engr also uh, explain these criteria, these structural integrity, that how much your bar should be extended. So I think so we also cover mgregor as well, and after that inshallah we will did numericals. So this is also explained by the mcgregor. Okay, now these rules will also be present there. Okay, so one important thing which he mentioned there, because only one of these need to be satisfied, the other recommends same thing. I will explain you that these three criteria cannot you need to satisfy. You need just one criteria to be satisfied. Okay, effect of discontinuity at bars. I explain you that when you cut the bar, there is tension, shear stress, concentration. So how we cover it? Okay, so basically I explain all those topics. Okay, also you can read this detail in this book also, in very important, okay, and very detailed way. McGregor represented more than Nilson. This is the same question which I did in lecture 9. So same question, he starts his you know he starts the cutoff point and cutoff locations of cutoff bars from this discussion. Okay, he 330 is the maximum, and they provide basically 5 number add bars, and then they cut 2 bars. Okay, and you can see this is the cross section at this point, and this is the cross section at mid. You have 5 bars, and it supports you have 3 bars. Same diagram. Okay, they cut 2 bars, and they just determine the moment capacity, which is 250. Now for 215 they determine the cutoff distance, that is 4.09, from same equation which I did in lecture 9. Clear? And he explained it in a more detailed way as Cormac Donut did this diagram. This is the envelope diagram. Okay, movement strength diagram you can say, and your movement strength diagram must be within this movement envelope. Okay, the dotted line show the actual movement diagram, and the continuous line showing you the movement strength diagram. So that is the same example which I did in lecture 9. So you can better understand if you read this example. Okay, I gave you short summary of those lecture. Okay, so there is it is in more detail, and I also tell you that the, the strength at B will be from C will be at a distance of LV. Okay, I will explain these things. Okay, so this is the shear effect. Okay, when you cut the bars, shear cracks will start in develops. So how you can adjust that problem, how you can justify that problem. Okay, so those discussion are there. Okay, after that inshallah we will in lecture 11 we will extend this lecture. Okay, we start from this point. This discussion is basically present. No, we start from this point where development of bars in positive movement regions. This diagram basically what kind of information these are very most important detail in this diagram. Okay, they are very most important detail. Okay, they basically showing you that when you are providing your full bars, 5 number 8 bars, that give you this diagram, and once you cut off your bars, your movement capacity will get reduced from that point to this distance. Here you can see this line, basically this dotted line you are you are watching, you are seeing, this is for number 8, 5 number 8 bars, and this diagram is basically, you can say, this dotted lines. Once you cut up your bars, so your movement diagram is there. But remember, basically this line give you the stresses, right? This give you the stresses. There are stresses is lower because there are 5 number 8 bars. Stresses are lower. Once you cut the bar, your stress become increased. Why? Now the tension become increased, and within D dash and D there are 5 bars. Once you cut the bar there are just only 3 bars. So on 3 bars, movement become increased, tension become increased, and due to tension increase, the stress will increase. So therefore, it goes to from D dash to C dash and D to C. Okay, so this is a very great information. Okay, and due to this stress increase, shear stress become increased, and due to that, we need some sort of other arrangement. Okay, inshallah, we will address those things in this topic, and after that, inshallah, we will direct them. Okay, so that will be inshallah our last theoretical topic. Okay, after that, inshallah, we will continue the exam. So for this time, I would like to stop my lecture. Okay, and then in lecture, inshallah, we will cover this rest theoretical lecture. Okay, if you have any question, any doubts, uh, basically I welcome. Okay, and I gave you my introduction as well. So mm, you can contact me and you can uh, take any kind of suggestion from me regarding